So it's my privilege to introduce Professor S.C. Arora. He is well-known personality in the field of mathematics. He has contributed a lot to mathematics education at all levels, from school to research in mathematics. He is superannuated from University of Delhi as head of mathematics department. He served for more than 40 years in the field of education. Until now, he is associated with different universities as a member of advisory committees of various academic institutions. Throughout his teaching, he remained involved in doing research besides teaching work. He has written more than 100 research papers published in reputed journals all over the world. His research is being referred throughout the globe. Many operators, namely slant-Haeckel operator, essential slant-Haeckel operator, slant-Topliss operators, and many more have been introduced by him. He has visited many countries and delivered many lectures in national and international conferences. He had been associated to UGC, CSIR, AICTE, DRDO, AIRI, NCERT, CBSC, DST, SCERT, and many public service commissions and universities. He is known to be a very popular teacher and successfully supervised 75 PhD and MPhil students, which is a rare combination of good teaching and good research. Today, he is going to speak on importance of fundamental theorem of algebra. Sir, Professor S.C. Arora, join the audio.
Thank you very much. Thank you. On screen. Thank you very much, ma'am, for the nice words that you have used for me. Thanks, everybody. Well, I begin my lecture on fundamental theorem of algebra. Before I come to the topic, I take you all to a court of law where a case is going on. The public prosecutor says that the accused is the real culprit because he was seen with the victim half an hour before the incident and nobody else met him after that. But defense lawyer says, gentlemen, your arguments are not logically correct. If we see them mathematically, they appear to be illogical. A politician, while advocating for his own political party, says that we are definitely going to win the election this time. But the leader of the other party says, that your arguments certainly do not fall in line with the mathematical logic, because the popularity is determined by the crowd that attends our meeting, and it shows that we are going to win the election this time, not you. A businessman, while advocating for his products, he says, with all mathematical tests, we are the best one because we are in great shape. See, everybody uses mathematics in one form or the other. Be a politician, be a mathematician, be a statistician, be a magician. See, everybody, a typist, a dentist, a orthodontist, everybody, in some form or the other, who does not use mathematics? Well, we are lucky enough that we are in that subject, which is omnipresent everywhere. Omnipresent because when we see, in the morning, you might have seen the newspaper vendor throwing newspaper at at the in various buildings at the first floor, at the second floor, and so on. He knows at what angle of inclination the newspaper is to be thrown to so that it reaches second floor, and also with what force the newspaper is to be thrown so that it does not strike the window pane. You might have seen housewives struggling and arguing with the street hawkers, and also must have seen the old ladies crossing the road. They look to the left, look to the right, and then compare their speed with the vehicles coming around. Only then they cross the road. Everywhere, at every place, they use mathematics. You know, well, I must say, I must congratulate each one of you that you belong to that subject, which is equivalent to so-called God, omnipresent everywhere, in every walk of life, in every sphere of life, in every shade of life. You belong to that subject. No. So, but in any case, at the moment, I am here to speak only one particular topic, that is fundamental theorem of algebra. Well, before coming to the topic, let me see you must have seen here uh, what the theorem is. Firstly, well, to history of fundamental theorem of algebra, and of course, I'll give only one proof. Although I'll tell you more than 100 proofs of fundamental theorem of algebra are available, and then as desired, I'll talk about applications also. Here it is written application, it should be application. Okay. What the theorem is: every non-constant polynomial with complex coefficient has a root in the set of complex numbers. Before coming to the topic, I take all of you to a class of students, undergraduate students, where a teacher is teaching, that every equation has got n and only n roots. And she or he begins with the proof. Says that suppose fx is equal to a naught plus a1x plus a2x square plus so on plus an not equal to 0 is an equation of nth degree. Let x equal to alpha 1 be a root of this equation. Then this equation fx can be written as x minus alpha 1 into f1x. And further, f1x is equal to 0 is an equation of n minus 1 degree and therefore has a root, and say let x equal to alpha 2 be a root of this equation. So f1x therefore can be written as x minus alpha 2 into f2x. And so fx therefore is equal to an into x minus alpha 1 into x minus alpha 2 into x into f2x, and so on. And further, see, fx is equal to an into x minus alpha 1 into x minus alpha 2 into x minus alpha n, and so on. See, there is no other root because, none of beta, satisfies this equation. And these are the only roots, and therefore it justifies that every equation of nth degree has got n and only n root. Right? Everybody is happy, including the teacher. But I must tell you, there are certain unhappy persons like me. I feel unhappy because for me, the first basic question is, that who has given a right to the teacher to assume that let x equal to alpha 1 be a root of this equation? Why this supposition? This is a big result called fundamental theorem of algebra. And that is the statement. Every non-constant polynomial with complex coefficient has a root in the set of complex number. Equivalently, every equation must have a root in the set of complex number. Every equation with complex coefficients must have a root in the set of complex number. This is fundamental theorem of algebra. You can state like that, or you can state like this, that every polynomial of degree n greater than or equal to 1 over the field of complex number has n and only n roots. These two statements are equivalent. And equally equivalent is that every polynomial of degree n greater than or equal to 1 over the field of complex numbers can be expressed as it can be factored into linear factors as some constant into x minus alpha 1 into x minus alpha 2 into x minus alpha 1. That is, if pz is equal to zn plus an zn minus 1 plus an minus 2 zn minus 2 plus so on plus a1 z plus a naught is a polynomial where the coefficients a naught, a1, an minus 1, they are real or complex numbers, then there exists a complex number z alpha such that p of alpha is equal to 0. Equivalent formation of this problem, the problem fundamental theorem of algebra, they are the following. See, every non-constant polynomial with real coefficient can be expressed as product of a real linear or real quadratic factor. That is, every polynomial with real coefficient has a complex root. And second one is, for each n greater than or equal to 1, every n cross n square matrix over C has an eigenvector. And that is, every linear operator on an n-dimensional complex vector space has an eigenvector. These two are equivalent formation. Please note the second one, because this is the form which we'll apply to practical problems. See, these two fundamental theorem of algebra is equivalent to the first one. See, because if fundamental theorem of algebra is proved, then if fundamental theorem of algebra is proved, then any polynomial with real coefficients can be treated as a polynomial with complex coefficients and can be therefore factored into quadratic and linear factors, and also realizing that any real quadratic will have complex roots in conjugate pairs. Again, see how one implies FTA. FTA, I will always mean fundamental theorem of algebra. If one is proved, then given any polynomial pz with complex coefficients, then one can construct a polynomial with real coefficients as pz into pz bar, and that is equal to 0. That is, pz mod square is equal to 0. Now, any root of the resulting polynomial will either be root of the original polynomial or the complex conjugate of a root. That means FTA is equivalent to the first one. Now, I'll talk about how FTA is equivalent to second. Suppose FTA is proved, and now suppose matrix A is A11, A12, A1n, A21, A22, A2n, and AN1, AN2, ANn. It is an n cross n square matrix over the field of complex number. Consider Zi minus A determinant is equal to 0. This would be determinant of Z minus A11, etc. That would be, see, the matrix is before you. And then, see, if we open this out, if we open this out, this is equal to Fz is equal to Zn plus An minus 1 Zn minus 1 plus so on plus A1Z plus A naught is equal to 0. That is, if lambda is a root of this equation, then lambda I minus A is singular. Therefore, there must exist some x non-zero such that lambda I minus A into x is equal to 0. That is, Ax is equal to lambda x. that proves, See, next, suppose second issue, how it, the fundamental, this is of course little calculations would be there, and I'll prove it by mathematical induction. Suppose second issue, then we consider any polynomial, fz is equal to zn plus an minus 1, zn minus 1, and so on, plus a1z plus a naught, where n of course is greater than or equal to 1. And all these AI, they belong to the set of complex number. I will prove this result by induction. Suppose uh, by induction, that is determinant of lambda in minus a, this will become equal to f log. I will prove this thing, where a is this matrix. If I consider this matrix 0, 0, 0, minus a1, 1, 0, 0, minus, and so on, for n equal to 1, what the polynomial would become? The polynomial would become z plus a naught. And in that case, I take the matrix A to be equal to minus A naught. And I find that lambda I minus A determinant is lambda I plus A naught, that is lambda plus A naught, and which is equal to F lambda. If I put n is equal to 1 in, there in the polynomial of nth degree. For n equal to 2, the polynomial would become z square plus a1z plus a naught. In that case, I will consider this matrix A equal to 0, 1 minus a naught minus a1. Lambda I2 minus a determinant, you can see it would become lambda a naught minus 1 lambda plus a naught, which is lambda square plus a1 lambda plus a naught, and which once again becomes equal to f lambda for n equal to 2. And suppose the result is true for n minus 1, because I'm using the mathematical induction. Therefore, I suppose that the result is true for n minus 1. That means the result has been proved for for polynomial of degree n minus 1. And now I come to polynomial of degree n. Fz is equal to zn plus an minus 1, zn minus 1, plus so on, plus a1z plus a naught. And f lambda therefore becomes equal to lambda n, and so on, putting z equal to lambda. Now, if I consider this matrix A, which is equal to 0, 0, 0, minus A naught, 1, 0, 0, minus A1, and 0, 0, 0, 1 minus. Please remember, I already know that the result is true for all, the polynomial of degree n minus 1. Then lambda I minus A becomes equal to this determinant, lambda 0, 0, this is A naught, minus 1, lambda 0, 0, plus A1, and so on, this one. And if I open that out, see, by first row, that is lambda of this determinant of order n minus 1 plus minus 1 raised to power n minus 1 into a naught of this determinant of order n minus 1. These two are determinants of order n minus 1. But the result is assumed to be true for any polynomial of degree n minus 1. This would be lambda of this one plus a naught. If I open that out, second determinant. When I open that out, second determinant, by the first column, it would be, only a naught. And that means lambda, because the result has been proved to be true for n minus 1, therefore, the value of this determinant, which is the coefficient of lambda, would become equal to this polynomial of degree n minus 1. Lambda into lambda n minus 1 plus a n minus 1 lambda n minus 1 plus a1 plus a naught, which on simplification becomes equal to f lambda. And therefore, determinant of lambda I minus a is equal to f lambda. Therefore, if a has a characteristic vector, then for some lambda, determinant of lambda I minus a, that is equal to 0. That means, therefore, fz is equal to 0 has a root in this. This establishes that the result is true by mathematical induction. These were the equivalent formulation. They were proved earlier, Well, now I come to history of fundamental theorem of algebra. It is a problem which had been troubling mathematicians right from the beginning of civilization. That look at, I begin with that some versions of the statement of fundamental theorem of algebra first appeared early in the 17th century in the writings of several mathematicians, including Peter Roth, Albert Girard, and René Descartes. All these mathematicians believed that a polynomial equation of degree n must have n roots, and the only problem was they believed to show that these roots lie in the set of complex numbers. See, it was a misconception, of course, to begin with, because their belief was that every polynomial must have a root. Uh, and the only difficulty was the existence should be in the set of complex numbers. And I begin with the next year, say 1702. A proof that the fundamental theorem of algebra was false, given by Leibniz in 1702, when he asserted that x4 uh, plus p4 could never be written as a product of two real quadratic factors. His mistake came in not realizing that under root I could be written in the form a plus ib, where a and b are real numbers. That happened, of course, in 1702. But 1742, Euler, in the year 1742, in correspondence with Nicolaus II, Bernoulli and Goldbach showed that the Leibniz counterexample was false. In fact, it is so. You know that under root I, of course, is a complex number that can be written in the form a plus ib. Now you know. But at that time, in the year 1702, it was not known. In 1746, Jean Lee Rondi D'Alembert, D'Alembert, the same D'Alembert, which you study is a D'Alembert ratio test, D'Alembert's principle, you see. And in the year 1746, made the first serious attempt at a proof of the fundamental theorem of algebra. He published his proof in the Researchers sur la calcul integral, History Academy Science Berlin in 1746. Page, of course, 182 to 224. This proof given by D'Alembert was not very rigorous and had several weaknesses. He used the following lemma. This is called D'Alembert's lemma. Suppose f is a non-constant polynomial and f z naught is not equal to 0, then for every epsilon greater than 0, there is some z such that z minus z naught mod is less than epsilon and fz mod is less than fz naught mod. If you really look at this lemma, this actually tells you that corresponding to every modulus, we can have a smaller modulus, right? This is what it is, modulus of the function. This is another version of that in the set of complex number on an open disk. If f is a continuous function, non-constant polynomial, then the minimum is never attained on the boundary. This is minimum modulus principle, exactly that thing. Another version of the same thing in this form, that if f is a non-constant polynomial and fz naught is not equal to 0, then for every epsilon greater than 0, there is some z such that z minus z naught mod is less than epsilon and fz mod is less than fz naught mod. D'Alembert proof of this lemma was not very rigorous because the results about continuity, differentiability, etc., they were yet to come into existence, and it was unnecessarily complicated. A simpler proof of the lemma was given by Jean Robert Argand in 1806. Furthermore, he also used that a continuous real valued function on a compact set achieves a minimum value, a fact that had yet not been rigorously proved by D'Alembert's lemma. You see, at that time, of course, because if you see, they are equivalent, Therefore, proof given by D'Alembert in 1746 was not convincing. In 1749, shortly after D'Alembert's proof, Leonard Euler published an algebraic proof of fundamental theorem of algebra by attempting to prove that every polynomial of nth degree with real coefficient has precisely n zeros in C. In 17 C set of complex numbers. In 1772, Joseph Louis Lagrange, the same Lagrange, which you study, Lagrange mean value theorem, Lagrange, in the year 1772, raised many objections to Euler's proof and pointed out many gaps. He used his knowledge of permutations to fill all the gaps in Euler's proof. However, one significant gap still remained. What was that? Existence of complex number which satisfied the existence of a root. That Euler and Lagrange both assumed that a polynomial of degree n would have n roots, and that the only thing to be proved is that these roots are nothing but complex number. You see, this is what exactly still fundamental theorem of algebra. Fundamental theorem of algebra not proved by 1772. Although assuming those things, many things were discussed. In 1795, Laplace in the year 1795 tried to prove the fundamental theorem of algebra using a complete different approach, using the discriminant of a polynomial. His proof was quite elegant, but unfortunately, in his proof also, the existence of the root was assumed. Then came the crucial year. I say why crucial year? It is 1799 when fundamental theorem of algebra was proved. The first person in 1799, the first person to notice these gaps was Carl Friedrich Gauss. He is credited with producing the first correct proof in his doctoral dissertation, which is submitted in the year 1799. About Euler-Lagrange proof, Gauss says the following: if one carries out operations and with impossible roots, as though they really existed, and says, for example, the sum of all the roots of the equation xn plus a xn minus 1 plus b xn minus 2 and so on is equal to 0 is equal to minus a, though even though some of them may be impossible to exist, which really means that even if some are non-existent and therefore missing, then one can only say that one thoroughly disapprove of this type of argument. See, where was actually the crux of this situation? It was very simple. See, before Carl Gauss, see, everybody was assuming the existence of the root, and they were only trying to prove that if we assume this thing, then we have the set of complex number where the roots would lie. But it was Carl Gauss, he said that no, the existence cannot be assumed. It has to be shown. About D'Alembert's proof, Gauss himself did not claim to give the first proper proof. He merely called his proof new. About D'Alembert's proof, despite his objections, he said a rigorous proof could be constructed on the basis of D'Alembert's lemma. Gauss' proof of 1799 was topological in nature. However, it does not meet our present day standards of a rigorous proof. In 1814, Jean-Libret Argan published a proof based on D'Alembert's 1746 idea and was the simplest of all the proofs. Gauss himself, throughout his lifetime, kept on working over fundamental theorem of algebra. And 2 years after Argan's proof, Gauss, in 1816, published a second proof which was complete and correct. In 1816 itself, Gauss gave third proof of the fundamental theorem of algebra, and in 1849, on the 50th anniversary of his first proof, gave the fourth proof of fundamental theorem of algebra. Since then, and even before, many mathematicians across the whole world, across the globe, have been working over the theorem and have been publishing various proofs using tools from various branches of mathematics. More than 100 proofs have come so far, and the recent most in it is 20 written. It should be 2021. 2021. The recent only recently a proof has come. The following proof: a proof of fundamental theorem of algebra using Hurwitz's theorem. It is published in Alien Math 1760 2021, number 1, page 38 to 39. The published by Mahmoodi and Muhammad Ghulam Mazde. Many mathematicians. Well, I'll now make you aware, with the development and of course, whichever, some collection I made to show to you Many mathematicians who got attracted by the problem and contributed to the solution of FTA include the following. The first one, different proof. First one in 1746, which I mentioned by D.L. Lambert. See, I begin with 1746. See, it is researcher Sir Calcul Integral History Academy Science Berlin. See, 2, volume 2, 182 to 224. Then Leonard Euler, 1749. See, the paper is before you. Research is Serla, etc. And the third one, Lagrange, 1772. Serla form dia resign imaginative this equation published over here. Then Carl Friedrich Gauss, 1799. It was published over here. 1799 proof. Although the proof was there in his PhD thesis, demonstratio nova. This is Italy's paper. Demonstration nova, ultra, theoretic, etc., etc. Next one. Fifth, argon in 1806. The paper is before you. It's signed. The representation, there's quantitative, imaginary, and so on. 1806. Then Carl Friedrich Gauss, again another proof by Gauss. See, demonstratio nova, ultra, theoretic, etc. See, reprinted, of course. Then 1920, Alexandra Ostrovsky, the research paper given in this journal. It was published in 1920. Then 1935, a proof of fundamental theorem of algebra, American Mathematical Monthly, 501 to 502. The next is 1947, one more proof of fundamental theorem of algebra, American Mathematical Monthly, 54, the 1947. Then Raymond Radjaffer, 1957, the fundamental theorem of algebra, American Mathematical Monthly, 64 to 582 to 585. Then R.M. Radjaffer, what another note just on fundamental theorem of algebra, American Mathematical Monthly, 71, 182 to 185. Then R.P. Boss, he has contributed a lot to this. Yet another proof of fundamental theorem of algebra, American Mathematical Monthly, 71, 180. The next is 1967, Wolfenstein, proof of fundamental theorem of algebra, American Mathematical Monthly, 853 to 854. Then 1967, Charles Befferman, an easy proof of fundamental theorem of algebra, American Mathematical Monthly, 854 to 855. Then Fraud Terkiselen, the fundamental theorem of algebra, American Mathematical Monthly, 83, 647. Then M.M. Dodson, 1984, a broad type coincidence theorem and the fundamental theorem of algebra, Canadian. It is Canadian Mathematical Bulletin. No. The next is A. Abian, 1986, a new proof of fundamental theorem of algebra, Caribbean Journal of Math, number 1, 9 to 12. Then John Stilwell, 1989, Mathematics and its History. It's a book. It is a book, actually. Mathematics and its History, published by Simon Verlauf. In 1989. In Abian and Wilson, 1990, a theorem equivalent to theorem of algebra. The name of the journal, page 17 to 18. Then William Dunham, 1991, Euler and the fundamental theorem of algebra, College Math, 282 to 293. Joseph Banich, 1992, another proof of fundamental theorem of algebra, American Mathematical Monthly, 99, page 246. Then Javier Gomez Caldron and David M. Wells, Why Polynomials Have Roots, College Math. It is another version of so-called fundamental theorem of algebra. Then Daniel J. Wellman, another proof of fundamental theorem of algebra, Math Magazine, 70 to 216 to 217. Then Daniel J. Wellman again, the fundamental theorem of algebra, a visual proof. It was unpublished, but Fortunately, I have a copy of the same proof. Although it was unpublished, but of course I had earlier. I'll let you know. I'll come to this. Uh, Benjamin Fine and Gerhard Rosenberger, 1997. The Fundamental Theorem of Algebra, Springer Perla, the new era. This book also contains 11 proofs. Then Michael D. Isra Sean, 1998, The Fundamental Theorem of Algebra, College Math, and this journal. And well, I don't read now because see, I want to talk about application. But in any case, you can see. I will just turn down the pages. Next, it is up to 2004. The next is 2005, 2006, 2009, 2010, 2011, 2012. Then it is 2012 again, 2013, 2014. Then 2014, 2014, and 2015. 2015. Wellman once again, Fundamental Theorem of Algebra, Visual Approach. See, 2015. Then see 2016. Vikash Chakravarti, an Indian, a simple proof of fundamental theorem of algebra, published in Math Student. Then it is 2017, 2018, and 2018 once again, 2018, 2018, 2019, 2019, 2019, 2019, and 2019, and then 2020 and 2021, the last one, which of course I have collected. But in any case, this is a big collection. You see, one can, if one is interested more and more about fundamental theorem of algebra, one can refer to this list and find out various and different proofs. So, well, at the moment, of course, here in this lecture, I would give you just one proof, see, based upon, because the proofs of all proofs of fundamental theorem of algebra necessarily involve some analysis, or more precisely, the concept of continuity of real or complex polynomials. Broadly speaking, they can be classified in five, to find out that the proofs of fundamental theory and theorem of algebra, they can be proved along following lines. The first one is complex analysis. Using complex analysis theorem, there are many approaches. See, one is, of course, Liouville theorem. One is Roche theorem. The other is, Picard theorem. I have picked up, and then the topological. Via topology, you can prove. Even via algebra, you can prove, only using algebra. Via probability, you can prove the probabilistic approach. And of course, the visual approach, Visually, you see assigning color to every complex number and finding out that where it becomes the darkest, that becomes the zero of polynomial. This is the principle, this is so-called the basic theory in visual approach, See, however, we give one proof based on analytic approach. That proof is based upon the Picard theorem. Picard theorem states that if there are two distinct values in the complex plane, which a given entire, a function, a complex function, which is differentiable everywhere, that is called an entire function. For example, a polynomial. For example, sin z. For example, cos z. They are all entire functions. If an given entire function, this does not assume exactly two distinct values. If there are two distinct values which an entire function does not assume, then this function must be constant. This is Picard theorem. See, now I come to proof of fundamental theorem of algebra. Suppose fz is equal to zn plus an minus 1, zn minus 1 plus so on, plus a1z plus a naught, and greater than or equal to 1, and ai are constant. See, this is given to me. Suppose let it possible fz is not equal to 0. That means 0 is never assumed for any z in C. Then my claim is that fz fails to take on one of the values 1 by k. Because suppose it assumes all the values. Suppose for each k, fzk is equal to 1 by k equal to 1, 2, 3. Then we have, see, fz, the polynomial, taking zn outside and taking modulus, z mod n is 1 plus an minus 1 divided by z plus an minus 2 z square plus an zn. And therefore, fz mod tends to infinity as z mod tends to infinity. And therefore, there exists r greater than 0 such that fz mod is greater than 1 for all z satisfying z mod greater than r. So, but this disk, although z such that z mod less than or equal to r is closed and bounded, therefore there must see fz mod q is less than or equal to 1 over there, then zk must have some limit point. That is, there exists a subsequent z and k such that z and k tends to z belonging to this disk, although z such that z mod less than 1. As f is continuous, fz is equal to limit of, see, z and k tends to z, so limit of f and k, and that becomes equal to 0 because, see, it is limit of 1 by k and I. Therefore, f, so if that is so, fundamental theorem of algebra is already proved. So therefore, fz fails to take on the value 1 by k for some k, for all z. So that means that, and also fz is not equal to 0. 1 by k also and not equal to 0 also. Exactly two values are not assumed by the polynomial, and therefore it must be constant. Because contradiction, because degree of fz, polynomial of degree greater than or equal to 1 cannot be constant. So this means that there exists some z naught belonging to z such that fz is fz not equal to 0. Well, this I have chosen one proof, and that too via one approach, that is via complex analysis. Although, as I have shown, there are so many considerations, so many things, so many lines available, so many approaches available, topological, algebraic geometry, and so on. You see, probability, where the fundamental theorem was proved to be true. See, during these years, beginning with 1702, and of course my list up to, see, the present age, 2021, the researches are going on continuously, going on, and people are finding out different proofs of fundamental theorem of algebra. Well, I come now to application. Fundamental theorem of algebra, what it is, in fact, you see, its equivalent form, that is, every square matrix has got every square matrix eigenvalue and therefore an eigenvector, and subsequently every square matrix can be transformed, can be by, using transformation, using it is similar to so-called a diagonal matrix. This is what the approach of application is. Fundamental theorem of algebra, particularly its equivalence to determining eigenvalues and eigenvectors of a square matrix and subsequently reducing the square matrix to diagonal form, has lot of applications to a broad range of sciences: physics, chemistry, biology, quantum physics, quantum mechanics, economics, and of course mathematics itself. We discuss, say, at least one of them in detail. What is problem one? Let us see. But the approach would be that which I am mentioning, reducing it to that. See, 2 hertz, please see this problem carefully. 2 herds of vicious animals are fighting each other to the death. During the fight, the populations xt and yt of 2 species can be modeled by the following system. System is dx by dt is equal to minus 4y and dy by dt is equal to minus x. Show that species 1 wins the fight given y0 divided by x0 is less than half. This is given to us, and we have to show using what? Using fundamental theorem of algebra, of course. Let us see how it can be written. Equations are dx by dt is equal to 0x minus 4y, dy by dt is equal to minus x plus 0y. Therefore, dx by dt, this can be written in this form. See, this is the first one, left hand side, is it is 2 cross 1 matrix, dx by dt, dy by dt is equal to, this is 2 cross 2 matrix, 0 minus 4 minus 1 0 xy. And that means if I put v to be equal to the vector xy, then it can be written once again, v by dt is equal to av, where a is equal to this 2 cross 2 matrix, 0 minus 4 minus 1 0. Now we have reached this situation. Now here comes the use of fundamental theorem of algebra. By fundamental theorem of algebra, A has eigenvalues 2 and minus 2 with corresponding eigenvectors minus 2, 1 and 2, 1. Of course, I have calculated them. You can see, obviously, as far as 2 and minus 2 are concerned, you can immediately see the characteristic equation becomes x square minus 4 is equal to 0. And the roots, therefore, x is equal to plus minus 2. And therefore, these are eigenvectors, eigenvalues 2 and minus 2. And eigenvectors minus 2 and 1 and 2 and 1 I have calculated by ax is equal to lambda x. By this, these eigenvectors can be calculated. You can find out. Of course, this homework I have done earlier. You see, let S be equal to this matrix minus 2, 2, 1, 1. Then this is an invertible matrix. And then S inverse becomes minus 1 by 4, 1 by 2, 1 by 4, 1 by 2. Again, the inverse has been calculated, Then we find S inverse AS becomes equal to 2, 0, 0, minus 2. It would be diagonal. This I have diagonalized. And therefore, A is equal to S 2, 0, 0, minus 2 S inverse. Right? Okay. Okay for everybody? Okay. I proceed further. This means, so therefore, differential equation system becomes dv by dt is equal to 2, 0, 0, minus 2 S inverse V. And that means, S 2, 0, 0, minus 2 S inverse V, bringing this S, which is in the right hand side, to left hand side, and it becomes S inverse. D of S inverse V divided by d2 and dt is 2, 0, 0, minus 2 S inverse V. That means 2, the right hand side. 2, 0, 0, minus 2 is minus 1 by 4. This is S inverse. Minus 1 by 4, 1 by 2, 1 by 4, 1 by 2, and vector V is xy. So therefore, S inverse V, inverse V, this is so S inverse V at the moment, S inverse V is equal to minus 1 by 4, 1 by 4, 1 by 2 xy is this here. Now S inverse V becomes equal to minus 1 by 4 and y by 2, x by 4, y by 2. And therefore, the upper one, this differential equation takes this form. D by dt of minus 1 by 4 plus minus x by 4 plus y by 2, x by 4 plus y by 2 is 2, 0, 0, minus 2 of the same matrix vector, minus x by 4 plus y by 2, x by 4 plus y by 2. And so, if we solve, this means that is, these are two differential equations now in this form. Which one? First one is d by dt of minus x by 4 plus y by 2, 2 times minus x by 4 plus y by 2, and d by dt of x4 plus y by 2 is minus 2 of x by 4 plus y by 2. See, these can be solved immediately because the right-hand side can be brought to this and taking, and dt goes over there. The solution would be, solutions are minus xt by 4 plus yt by 2 is minus x0, putting t is equal to 0, the value of this constant is this, minus x0 by 4 plus y0 by 2 e raised to power 2t. And xt by 4 plus yt by 2 is equal to x0, and this is second equation, x0 by 4 plus y0 by 2 of e raised to power minus 2. And therefore, yt, on adding xt cancel out, and yt becomes equal to, yt is equal to minus x0 by 2 plus y0 by 2 e raised to power 2t plus x0 by 4 plus y0 by 2 e raised to power minus 2. And which on simplification becomes yt is equal to 1 by 4 minus x0 plus 2 by 4 e raised to power minus 2t plus 1 by 4 x0 plus 2y4. Look at this expression, the last expression, carefully. We are given that 2y minus x0 plus 2y0 is negative. So therefore, this becomes, see, as t increases, see, this therefore tends to, this becomes negative, right hand side becomes positive because that is positive, and we therefore obtain, and xt, of course, this given 2y0 minus x0, this is less than 0. Therefore, as t increases, yt keeps on decreasing and ultimately tends to 0. When it becomes 0, when this expression becomes equal to 0. That means e raised power 4t is equal to this and t. That means at this time, 1 by 4 log of x0 plus 2y0, x0 minus 2y0, this becomes equal to 0. And when t becomes equal to 0, but xt remains greater than 0, and you also see that xt in that case after that time becomes constant. If you look at the equation, dy by dt, dx by dt was equal to minus 4y. So when y becomes equal to 0, dx by dt becomes equal to 0. That means x becomes constant. Right? See? Well, only one more small application, see, that is, problem 2. Suppose you want to open a saving account.
Okay, man. Okay.
क्या हुआ? खत्म करना. In example 1, the matrix A is 2 cross 2. In general, in practical problems, the matrix may be n cross n, where we apply FTA to find eigenvalues and eigenvectors to diagonalize. However, for n equal to 1, this is the problem. Suppose you want to open a saving account and you find out that, there are discrete banks and, of course, and this is continuous bank also. Which bank? This fundamental theorem of algebra, of course, to 1 cross 1 problem, you find that even if the discrete bank gives you 7% interest and continuous one gives you 6% interest, you find that fundamental theorem of algebra can be applied to find out that the discrete bank is better. Thank you very much for all that. Thank you for patient listening.
Thank you, sir, for giving the knowledgeable algebra. Also, expressed beautifully the proof of fundamental theorem of algebra. With this, sir, I would like to express my sincere thanks for enriching our knowledge about the various authors who gave the proof of fundamental theorem of algebra. This proof is very important, and also their result is used many times. Sir, you have told us about the applications of this theorem, which very few of one knows. So, I wish to express my gratitude to you, sir. And there is no query in the chat box. So your lecture is fantastic, and everybody clear it. So thank you so much,
thank you very much.
Thanks a lot, sir.
Thank you very much. Thank you. Thanks for all these. Thanks for the nice words. Thank you very much.
Thank you, sir.
So, even if there is any query, you see, I am always available. See, anybody can contact me and find out, you see, what the problems are.
Okay,
no
sir.
problem as such.
Okay, sir. Okay, thank you, sir.
Okay.
Now, we are moving towards next session.